Hello everyone, you're welcome to this channel once again. Today we have a peculiar question surrounding how to calculate the natural frequency of a system. Now let's read through the particular question we have today in the figure. In the figure below, a disk has mass m equals 100 kg and radius of r 5 meter, and the moment of inertia about the mass of this particular disk I, which is moment of inertia, equals mr squared over 2, and is attached to a block of mass 300 kg, which rolls across the surface. The block is supported with a spring with a stiffness of K equals 3 times 10 to the power 5 Newton per meter. If the disk rolls without slipping and the block moves without friction, calculate the natural frequency of the whole system. That is, calculating the natural frequency of the whole system here, represented in the schematic diagram. Now, how do we approach this particular dynamics problem? First of all, by pulling out all the parameters, we have m, the mass of the disk rotating without slipping, which is 100 kg. We have the r, that is the radius of the disk, which is 5 meter. We have I, which is the moment of inertia of the disk system, which is mr squared over 2. And we have the mass of the block attached to the disk, which is 300 kg. Don't let us forget the spring attached to the block of mass rolling, which is given also, which is 3 times 10 to the power 5 Newton per meter. Now we are supposed to calculate the frequency of a system, which is Wm. How do we approach this? First of all, by using the equation of the potential and the kinetic energy of the whole system. How do we pull it out? By using U, which is potential energy of the system. U equals 1 over 2 over Ks squared. And knowing fully well that as the disk is rolling, the equation of the dynamics of the rolling disk to the block equals X equals R theta. So by differentiating it using calculus, it becomes S dot equals R dot R theta dot. And by squaring both, that gives us S dot square equals R square theta dot squared. Now, by using the formula of the kinetic energy, which is half K squared, and adding it to the kinetic energy, which is T, given here, T equals half to the product of the mass of the block to the S dot square plus half to the product of the mass of the disk, m, small m, to S dot square plus the rotational energy, that is half of I theta dot square. And we are given that I equals mr squared over 2. So the equation becomes T equals half m dot square s plus half m dot square s plus half into bracket mr square over 2 into bracket theta dot square. and knowing fully well that x squared equals r squared theta dot square from the reference of the dynamics, we can input it into this particular equation. That becomes T equals half m, that is the mass of the block, to s dot square plus half m, that is the mass of the disk, to the s dot square plus 1 over 4 m s dot square. So our equivalent kinetic energy T equals half m x dot square plus 3 over 4 ms dot square. Now, by adding both the potential energy and the kinetic energy of the whole dynamic system here, it becomes the differential of T plus U equals the differential of half m dot square plus 3 over 4 m dot square s plus half ks square. That gives us this particular equation. So by pulling out s dot square from the equation, we have x dot square into bracket m s dot plus 3 over 2 ms dot square plus kx. And knowing fully well that our x dot equals 0 here. So therefore, by equating s dot equals 0, we have ms dot dot plus 3 over 2 ms dot plus kx. So by pulling out our x dot dot outside bracket, we have dot big M plus 3 over 2 small m x dot dot in bracket plus ks equals 0. Now, by linearizing both equations to the standardized dynamics equation, which is ms dot dot plus cs dot plus ks square, we can deduce that our m equals this particular one in the bracket, and our k equals k. So therefore, m equals m plus 3 over 2m, which is given here, and k equals k, which is given here. Now, by slotting these particular parameters or value into the standardized equation for the natural frequency, which is Wn equals k over m. That is Wn equals the root of k over big M plus 3 over 2m. Now, our Wn, using the whole parameters given and slotting them into this particular equation, give us 25.82 radian per second. Now, using the Wn equals 2 pi L equation, we can deduce that our frequency in hertz, not in radian per second this time around, becomes Wn over 2 pi. So that gives us 25.82 over 2 multiplied by 3.14. That gives us 4.1 hertz. Once again, our calculated natural frequency for this particular system becomes 4.1 hertz. Thank you very much.